New video, new topic. And this is going to be transformers, which we haven't really talked about before in any of these courses, so we need some introduction. And for that we can go into the Intro to Electrical Engineering playlist, link in the description, and we manipulate that relationship between magnetic fields and currents to create magnetically coupled circuits. So we're going to be looking at mutual inductance, transformers, what they are, how they work, symbolic notations. Then we're going to look at the dot convention. Now, thanks to Faraday, we have a relationship between a voltage that becomes induced for a coil of wire and how that corresponds to a magnetic flux. So what we can say is that the voltage induced is equal to the number of turns in the coil and then the time derivative of the magnetic flux. And then we group this N d phi dt, call that L, and that's our inductance. So essentially, if we have a circuit like this on the right where we have some current source, we have a coil of wire, that current induces a magnetic field. Magnetic field changes with time as the current changes with time, and we induce some voltage. Or in a one-sentence explanation, current induces a magnetic field and vice versa, which is great for discovery, but how can we use it to benefit us? Well, let's consider two coils next to each other. So if we have some current that's changing with time, we have this coil of wire with N1 amount of turns and inductance L1, we know that we're going to produce some field phi 11, and we're going to have some voltage V1. Now, if these coils are pretty far apart, don't really have to concern ourselves with much, but if they're pretty close such that this second coil is meaningfully in the way of the magnetic field produced in the first coil, and that's a real blanket statement to say meaningfully in the way. But if we have this condition, then we have the magnetic field from coil 1 getting induced into coil 2, which creates a voltage. So what we can loosely say is that the magnetic field from L1 leaks into L2 and induces a current, or I1 produces some voltage via L2. And what we can say is that the voltage over inductor 1 is equal to N1 times the time derivative of the first flux, where in this case phi 1 is simply going to equal phi 11. And we can also express that as the inductance times di1 dt. Now the voltage over the second inductor is going to be equal to N2 times d phi 12 dt, where this is that contribution of coil 1 to coil 2 that we just talked about. And we're not going to relate this to the second inductor, L2, but we're going to call this instead the mutual inductance. So we're going to call some mutual inductance M21, which is corresponding to the second coils in the inductor and in the flux from coil 1 to coil 2. That's going to be our mutual inductance M21. So this term would actually be equal to M21 times the derivative of I1. And if we flip the circuit to the other side, we get a symmetric term, M12 equal to N1 times the derivative of phi 21 with respect to I2. But assuming conservation and ideal systems, we can say that M12 is equal to M21, which is just going to be the mutual inductance, and that's given in the unit of henries. So a transformer is essentially two coils of wire that are close enough that the current of one can impact the current of the other coil. So if we look at a typical circuit schematic, what you're going to see is something that looks like this here on the left, where you have a voltage source. We call this input the primary. So you'd have a primary current and then a primary winding, and you'd have L1. On the other side, you would have a secondary, where you would have a secondary current, and then you might have a load of some kind, and then you have your second inductor. Now those are expressed by this coupling of M, where M is that mutual inductance. Now as far as transformers, there's a few variations you might see. So you have an air core transformer, where you just have two coils of wire and air in between. Now you might also get these vertical lines, which symbolize an iron core, and that has a strong impact on the performance of the transformer. And then you also have something called a variable transformer, where you get this arrow going through. Sometimes you might get the iron core lines, depending on what kind of transformer you're looking at. But this is a variable circuit schematic, so it means the value can change on the fly. And lastly, we want to look at something called the dot convention. Now, the dot convention can get a little bit confusing, but because this is an advanced circuit analysis course, we have to deal with advanced topics. So the dot convention deals with dots on the primary and the secondary for the transformer. Now, in general, current entering a dot on one side induces a positive voltage reference at the dot on the other side. And what this ends up meaning is that the primary and the secondary voltages are in phase. Now, conversely, the current leaving a dot on one side induces a negative voltage reference at the dot on the other side. So you get the primary and the secondary, and they're out of phase by 180 degrees. Now, this convention is very nice for these two situations, but sometimes you have problems labeled with polarities and currents in all sorts of directions and dots in all sorts of directions. So we're going to try to avoid confusion and simply have 6 examples, which should get most of the problems, if not all the problems that we look at, to be evaluated. So from all of these 6 combinations, there's a few things that you can take away. There's 2 rules, and that should give you the general notation for how to do the analysis. And those 2 rules are as follows. If the current goes into a dot on one side and out of a dot on the other side, it's in phase. And if the voltage polarity matches at the dots, the voltage is in phase. So let's look at the first one. We have current going into a dot, and we have current going into a dot. That doesn't really line up with this, so the current would be out of phase. Now the voltage polarity at the first dot is plus minus, and the voltage polarity at the second dot is minus plus. So these don't match, which violates this condition, so the voltage is out of phase. Let's pick another one at random. Let's go top right. We have current going into a dot, current going out of a dot. Matches our condition, current is in phase. Now at the dot, we have a plus, so that would be our polarity. And at this dot, we also have a plus, so the voltage is in phase. And now let's go bottom right. So if we draw a little ghost source, we could also say that current is going out of a dot here and out of a dot here. So we're out of a dot on both, so we would say that the current is out of phase. And at each one of the dots, we have a minus sign. So the voltage polarity matches, so the voltage would be in phase.